Okay, so let us begin with the normal distribution once again. So in the last lecture we have seen few features of normal distribution function. So today I am going to tell you few more things related to it. One unique characteristic of normal distribution is this. So this will not prove here, but this is a very unique characteristic. You may find it is useful in your uh, project work or maybe research work, that any linear combination of
So
normal,
screen,
yes,
so screen is
normal
black.
distribution.
So the
Screen is
screen
not visible,
is
So
it
it
is
is
very blurred.
very blurred. Okay, then I think again I have to restart it. Sorry, wait for a few minutes. I'm restarting it. Am I audible now?
Yes, sir, you're audible.
Hello? Audible. Okay. Let us see. Is the screen visible now?
Yes, sir.
Okay. Good. Okay, any linear combination of normal distributions also follows normal distribution, and if I mean any linear combination of a set of random variables follows normal distribution, then they individually follows uh, normal distribution.
Set.
Okay, so that means, say for example, if sum over ai xi follows some normal distribution, whatever mu sigma square. So first of all, if xi follows normal distribution, then maybe I equals to 1 to n. Sum over ai xi will follow normal distribution. This is one thing. Another thing, if sum over ai xi follows normal something for all ai belongs to R, I running from 1 to n, then xi follows normal, some mu some sigma square. So this is the story, and this is the unique characterization of normal distribution. Okay, another thing related to it, have you heard about the mixture distribution or used something called mixture distribution in any of your project? So mixture distribution and linear combination of distribution or random variables are different things. Okay, so be careful. This is a very red alert note. That say x1 follows some distribution f1, x2 follows some distribution f2. Okay, then linear combination of x1 and x2 is say a1 x1 plus a2 x2. This is some another new random variable altogether. Okay, but this is case 1. Case 2, mixture distribution of x1 and x2 with is the screen getting blurred again?
No, sir.
No.
Okay. The mixture distribution of x1 and x2 with probability say P1 and P2 respectively. Definitely in this case P1 plus P2 equals to 1. Respectively means this thing. This is a completely separate story. That you draw a random number, if it is less than, so I should write here, if it is less than P1, then draw sample from x1, else, that means if it is greater than P1, it is entering in the range. So say for example, up to this much is P1 and this entire length is P2. So P1 plus P2 equals to 1. So else draw sample from x2. So this thing and this thing, here you can say this is P1, this is P2, but writing P1 into x1 plus P2 into x2, this y variable and this variable, they are not same. Both are random variable. They are not same. Structurally, they are different. People often do mistake. They call mixture distribution as this. That is not. This is linear combination of random variables, and this is mixture distribution. Not only that, you can do the linear combination of more than 2 random variables. You can do the mixture distribution of more than 2 random variables. You need to have a probability vector for that. That's it. Okay. So what will be the common thing for both of them? Can anybody tell me? Based on whatever we have developed, you should be able to tell me this thing. What will be the common thing? It has different distribution, it has different distribution. So if you want to draw the distribution, say for example, if you want to say, suppose this is F1 distribution and this is F2 distribution. Okay. So if you do a linear combination of them, then yeah, there will be some distribution which might follow like this. So this is linear combination. But I don't have any other color. Let me see. Okay, so let me see. Yeah, but if you go for the mixture distribution, you might find something like this. Okay. So in this situation, can you tell me what will be the common for both of the distributions? This linear combination and the mixture distribution. Any property you can identify that should be same. Rest of the thing we cannot guarantee. And mixture Gaussian is a very common thing. this thing, mixture distribution and mixture Gaussian is a very common thing to implement. You don't know from which model the data are coming. You can assume that there are few possible models and it can come from any of the model with certain probability. So you need to go for mixture distribution. This is a very common thing in your machine learning problem. So can you tell me what could be the common thing between this mixture distribution and the linear combination of distribution? Any clue? Only the expectation will be same. Guaranteed. Expectation will be same. It is nothing more is guaranteed. Other moments, nothing can be guaranteed. Expectation will be same. Mean of this random variable and mean of this random variable, they will be same. If the linear combination, the coefficients and the probability vector are same, then it will be same. If the coefficients are same. Okay, so you can see that mixture of two normal distribution can be bimodal. Bimodal means it can have more than two modes. But linear combination of normal distribution is again a normal distribution. It has one mode.
Sir?
Yes, Bolo.
Sir, you said that expectation will be same if they have same coefficients.
Same coefficient means here, say for example, if you go by 2, so
and
A1 equal to P1, A2 equal to P2.
Yes, sir. Then
Got it?
shouldn't the graph for both be same? Like
No. The construction is different. Construction is different.
Okay.
So here what you are doing, here you are taking two random number always, and then you are summing them up with P1 and P2 multiplication. Here you are not drawing two random variable always. You are flipping a coin. If it is say for head, you are going for x1 and take that random variable, observation from that random variable. If it is tail, you go for x2, then take the observation from the other random variable. You are not generating pair of random variable here, x1, x2. But here you are always generating pair of random variable x1, x2 and take their weighted sum. That is the constructional difference. Is it okay?
Yes, sir.
Hello? Got it?
Yes, sir. Yes.
Okay, very good. Okay, so for note that linear combination of normals is a normal, hence unimodal, but mixture of normals need not be normal and can be multimodal. That means this kind of peaks will be there. This is a clear-cut thing that you can distinguish, and you should not, mess up with these two notions. Okay, we have talked many things. Maybe this is not in your syllabus, but still, considering the new age of statistics, I should tell it in your class. Linear combination. Okay, standardization. This is a very common term. I should tell standardization. So, if x follows normal mu sigma square, then z equals to x minus mu by sigma follows normal 0, 1. So this transformation is known as the standardization. This is a very common term and without saying anything. So standardization typically means subtract the mean and divided by the standard deviation. Whatever may be the random variable, if mean variance finite, you subtract the mean so that it will become mean 0, divided by standard deviation, it will become variance 1. That doesn't guarantee that it will follow normal distribution. If x follows normal distribution, if you standardize, it will follow normal 0, 1. Otherwise, you will have mean 0, variance 1 random variable. Okay, that means the standardized thing. Acha. Now, let me talk about the moment generating function. Okay, one student has raised question that how to prove that pair of some laws of some random variables through moment generating functions. So let us discuss about it. Moment generating functions, MGF. Okay, very good. Oh, so I need a separate page. Okay, before we go for moment generating function, let us assume this thing, it will be useful there, that let x has MGF is m is to e to the power tx if exists. Okay, then y equals to a plus bx has MGF is, it is trivial that you can get this thing, expectation of e to the power ty, which is e to the power a plus b at plus btx, expectation of that. I can write this thing multiplied with 3. So e to the power at is constant, then expectation of e to the power btx. So that means this is the thing, e to the power at into m x bt according to the definition. Is it clear? This is the thing we are going to use. Hopefully this is not a very difficult job to understand. Now from here, okay, so let us talk about normal, then I will talk about the sum law of random variables as well as the normals together. So now from here, let us try to see that, so let z follows normal 0, 1. Then what will be the mzt is expectation of e to the power tz, correct? So e to the power tz, what you will get from here is e to the power tz, e to the power minus half z square root 2 pi integration minus infinity to plus infinity dz by definition. Okay, clean and clear. So now if you have this thing, then how can you do the adjustment? The trick is this, you want to express the exponent in such a way that it will become a complete, a perfect square and some added term. So please check whether you can write this thing in this way or not. Integration minus infinity to plus infinity e to the power minus half okay, z square minus two tz, that is all right if I take it inside 2 tz plus t square, that means within bracket half t square my negative sign, and I am adjusting that thing with plus t square by 2 all in exponent, and here root 2 pi, sorry, dz. Check whether it is okay or not. Is it clear? Now you notice this thing that I can write e to the power t square by 2 outside and e to the power minus half z minus t whole square divided by root 2 pi dz. Tell me what will be the integration of this part?
One.
If I integrate minus infinity to plus infinity, what will be this integration?
One.
1. So e to the power t square by 2 into 1, so it is e to the power t square by 2. So this is the moment generating function mzt equals to e to the power t square by 2. This is the MGF of normal 0, 1. Okay. Now if I say that x follows normal mu sigma square, then I can write that or define in this way that x equals to, I should write this is d, well, but let us at least go by this notation, is mu plus sigma z. If z follows normal 0, 1, then x follows normal mu sigma square. I hope it is clear to you now. Now can you please tell me what will be the MGF of x, which is mxt, from this result that you have just seen?
E to the power mu t
Sigma t
times
plus t squared.
So e to the power mu t plus half sigma square t square. Yes. So this is the answer. In one line you can get from this result very easily. Okay. So this is the moment generating function x following normal 0, 1. Sorry, mu sigma square. Okay. Another thing you notice from here that this quantity, if you write mzt is e to the power t square by 2, if you expand the E series, it will be t square by 2 whole square, whole to the power k into 1 upon k factorial. K is running from 0 to infinity. Is it okay? So these expressions are t to the power 2k divided by 2 to the power k into k factorial. Okay. So now if you want to get any order moment, rth order moment, you can differentiate this expression and put t equals to 0. So mu r for this random variable is del del t mzt at t equals to 0. Now quickly tell me what will be the expression of mu r. So okay, so when R is even, when R is odd. Tell me, what will be the expression?
Sir, should the mu r equal to del to the power r by del t power r?
Sorry, R, yes, R times. At t equals to 0, you have to evaluate it.
Zero.
If R is odd, then it will be 0.
R is odd, then it will be 0. This is a very fundamental observation. If R is odd, then it is 0. This
Sir,
one?
in 1 if it is even. The 1.
1 means R equals to 1.
No, sir, R is even, I am saying. R is even.
R is even. Then you will have
1 upon 2 power r.
no. It will not be 1. You will get something. Okay,
Sir,
so
1 by 2 power r.
From here you will get some expression. It will
Sir,
not be
1
always
upon 2 power r.
1 upon 2
power r.
Wait, let me check. Sigma, some expression should come in general. So it should.
Sir, r factorial by r by 2 factorial into 2 power r by 2.
Well, so let me just give you this thing to check. This one I'm leaving as a homework. Let me just tell you from here that 23, that if y follows normal 0 sigma square, then expectation of y to the power 2k should come in this form: sigma to the power 2k 2k factorial divided by 2 to the power k into k factorial. Okay, this thing you verify. So from this moment generating function, you can easily get the moment generating function of normal 0 sigma square, and from there you take the derivative and get it. This is your homework. Okay, so this thing you should get. Okay, so the another thing that question was asked, that sum of random variable, that laws it holds. So here in general, so if say x and y are independent random variables, then say define z. I am simply defining so that x plus y in this format, and x, assume x has mgf mxt, y has mgf myt. Then if I want to express the mg of z, I think it will be pretty easy for you now. Independent is needed for the this one to hold, that expectation mgf of z is say mzt is expectation of e to the power tz is same as expectation of e to the power t x plus y equals to expectation of e to the power tx into e to the power ty, and all they are given independent. So this product law will hold that we have assumed to work, that e to the power tx into expectation of e to the power ty. So as a consequence, you will get m xt and m yt. Okay, so this is in general to hold. Now all those results that we were claiming, so first let us start with given this, let us start with normal, that example x follows normal, say mu1 sigma 1 square, y follows normal mu2 sigma 2 square, and z equals to say x plus y. Then mzt is mxt into myt. Okay, so mxt, what it will be? E to the power mu1 t plus half sigma 1 square t square into e to the power mu2 t plus half sigma 2 square t square. So if you combine them, e to the power mu1 plus mu2 t plus half t square sigma 1 square plus sigma 2 square. Okay. Now you can see from here we can conclude that z follows normal mu1 plus mu2, variance is sigma 1 square plus sigma 2 square. Okay, so this is the way you can go for. So similarly, if you go say x to x follows binomial n1p, y follows binomial n2p, z equals to x plus y, then mzt equals to, what is the moment generating function for binomial? We have done it. Please tell me quickly. P into e to the power t, right? Plus 1 minus p. Is it okay? Check. P into e to the power t plus 1 minus p whole to the power n1 into p into e to the power t plus 1 minus p into n2. So p into e to the power t, please check whether I am correct it or not, n1 plus n2. That implies z follows binomial n1 plus n2 p. Any query, any doubt in this method? Hello? Especially the student who has asked me the question today over mail.
No, sir.
Okay. So similarly, you can have all those other results, 3, that x follows, and they are independent, okay? They are independent. So x follows Poisson lambda 1, y follows Poisson lambda 2, independent, x1, x plus y follows Poisson lambda 1 plus lambda 2. Same method. 4, X follows gamma alpha 1 lambda, Y follows gamma alpha 2 lambda, X plus independent, X plus Y follows gamma alpha 1 plus alpha 2 lambda. What else? Okay, 5. X follows negative binomial R1 P, Y follows negative binomial R2P, independent X plus Y follows negative binomial R1 plus R2P. Anything else we are missing? I think this is the sum law, or the distribution is preserved under addition. Okay. So don't forget, these are very useful tools for statistical analysis. Okay. Any other queries? Tomorrow we will do all those things with different functions and some problems also at the same time. So today let me just briefly any other query do you have? Whatever normal distribution we have done. Anything I am forgetting? Okay, MGF done, standardization done, linear combination done, table I have to show. Okay, anything else you have in your mind to ask or any doubt?
So the normal 0, 1 can be many other functions apart from e power minus t square by 2 by root 2 pi.
No, say again, please. I didn't get your question.
So in the previous example, you took normal 0, 1 as e to the power minus t square by 2 by root 2 pi, right?
Normal 0, 1. This is the PDF. This
Yes,
is the
we
e
can
to the
take
power
some
minus.
other function which gives which is symmetric and has PDF. I mean the probability
No,
one, right?
no. Random variable is unique. I have told you, random variable is uniquely characterized by its either PDF or PMF or CDF. And moment generating function exists, then moment generating function, characteristic function not in your syllabus, then characteristic function. So any curve, this is the PDF. If the PDF is this, then only it is normal distribution, or PDF is e to the power minus half, that we have already told you where it is. Well, I have not precisely written, but in this form, 1 upon sigma phi of this. So then that this is the PDF of normal distribution. Otherwise, any symmetric curve is not normal distribution. We will see the example tomorrow. There is Cauchy distribution, symmetric, but is a notorious distribution because none of the moment exists. There is Laplace distribution of double exponential distribution, that is also symmetric but not normal distribution. So, have I answered your query?
Yes, sir. If we take some other function, it will be some other distribution.
Other distribution, definitely. Yeah, it is characterized by its PDF. Okay. We will see all those things tomorrow. Cauchy distribution definitely we will do tomorrow. Okay, so before we go, we need to at least once in your life you need to see the normal table. Nowadays, most of us don't use it because we have the software. But if you go from a classical setup, the table will be there. So is it properly visible? Is it visible more or less at least?
Yes,
I
sir.
didn't get.
Yes, sir.
Okay. So here you see that whenever you will go for seeing a normal table, you must have these two expressions, that how the table is or what the table is representing. Most of the book represent in this way. It calculates probability x less than capital X less than equals to small x. That means area under the curve, this red region they represent. Okay. Now some of the books represent the probability for x greater than small x. That means this white region probability, upper half probability they represent. But most of the cases, so whenever you will see any table, you first look at its header. What is written in the table, that will be either diagrammatically or by proper expression it will be given there, what probability are tabulated there. Okay. Now it is for the standard normal distribution always given. Okay. So standard normal distribution up to 0, 50% of the distribution, so probability is 0.5. Now this row is for 0, if this is for 0, then 0.01, 0.02, 0.03, 0.04 up to 0.09. Then you come for the next row, 0.10 this probability, 0.11 this probability, 0.12 this probability, so on and so forth, 0.19 this probability. So it completes. Then you go for 0.20 this probability, 0.21 this probability, 0.22 this probability, 0.23 this probability, so on and so forth. Now sometimes it is also given that certain probability is given and you need to find out for what x value you are getting that probability. So say for example, I am giving you that 95% probable, that means 0.95. So can you please identify for what value it will have 0.95?
So 1.65.
1.65.
1.6. Now there is a catch. 1.6. 1.6. Okay. 48. 3. 9495 9505. Okay, so somewhere here, right?
No, sir.
No, not there. It should be 0.995. So it should be in between these two, right?
Yes.
Yeah. So 1.6. Yeah, it is either 1.64 or between 1.64 1.65. So you can, if you see the PDF, I think I have given this number 1.64 as I have given this number. Typically this number is used many often, and similarly you can cross check that for 1.96 the value will be approximately 0.975. So you can cross check from here that 1.96, 1.9, then you go up to 6. Yeah, it is exactly same number given. So is it okay? How to see the normal table? Any query? And most of the cases you will see that upper half of the table given, not the lower half. So if you need to figure it out, what will be the value for the lower half, you need to use this symmetric identity, the 7th identity that is given. This symmetric identity you have to use, and from there you have to figure it out. There is no other alternative. Or you can use any software. Okay. So any query? How to see the normal table? because
Sir,
in your exam you might have to see.
sir, suppose we want to calculate value at 1.64. So how will we integrate the function? Means can we do it by hand or it is through
No, no,
means
look, it doesn't have a closed form integration. If we had a closed form integration, already I have written for you.
okay, sir.
We don't have a closed form integration. This is the table. When we were student, we didn't have this computer or software. When I was student like you in the second year, so we had this biometric of volume. So this kind of volume and even more finer tables are available there. Normal distribution table, T distribution table, chi-square distribution table, F distribution table, Pearson characteristic table. All those tables are there. Random number table. So you open that book and you go line by line and check it, figure it out from there. And not only that, in that table, that Biometrica book, they also have the formula how to do the interpolation between these numbers also. So if you have to find out something, say for example, for 1.573, 1.5 for this number you want that probability. So the formula is given there how to interpolate the number appropriately. So you have to do that, and then that number you can use for your exam or whatever maybe. And in your exam you have to do all those things. In our case, maybe not in your case. So that life was not that easy in those times. So at least let me just tell you one example in R, which is pretty easily available and free source software. You can use it. How you can use that one for normal distribution. So say for example, if you want to check that how much time, okay, so first of all, just help file, if you go for this R norm, here you will get these four functions are usually available for any distribution, whatever package available, these four functions. D norm is for density function. You give the value of x, you will return the value of the density function. Achha, P norm will calculate the probability up to that point. Q norm, if you provide the probability, it will return the value of x. That means if you where it is, if you provide no, yeah, if you provide the probability, then this x value will be supplied, and then R norm to generate random number. Okay, so here our interest is Q norm. So Q norm. So say for example, I am looking for the x value for point say 75. So x 775. So or x 0.75. If I denote in this way, then Q norm, the probability I need to assign. If you go by tab, you need to assign the probability 0.75. Then again you go for tab mean. For standard normal we want. Then again for standard deviation, remember we in book or in question paper or in pen and paper we write normal mu sigma square, but most of the software consider normal mu sigma. Don't do this mistake. Most of the software consider normal mu sigma. If there is a scale parameter, they use as a scale parameter. Sigma is a scale parameter. So SD 1. So now if you run this line, so x 0.75, yeah, you can see that it is 0.6744. So let us see from the table whether it is how good it is. 0.75, 0.7575, how much? 7.2, 7.5.1, 7.4.8. Something here, and what is here? 0. 6.7. Okay, 6.7, then 4.4. So what I can get, that 0.6, then 0.67, up to that much we can get, but after that from table we cannot figure it out more precisely, but software can give you that thing. Is it okay? Now if you go for x 0.25, what will be the value? Can you tell me? What will be x 0.25?
Minus 0.675, that value.
Yeah, let us see. So you are correct. Because of the symmetry, you will get that thing. And software will give you everything, whatever value for you want. But if you use the table, you need to use that symmetry. Okay, it's good time to stop. Tomorrow we will do the properly. We will define, if you have a function of random variable, then how from one PDF to another PDF you can get, and we will use that thing extensively in tomorrow's class. Okay, and I think by Wednesday or Thursday the review of your test will be open. We got stuck because of some technical problem of some students, so we got delayed, but by Wednesday or Thursday it will be, review will be open. Okay, thank you. Anything else?
Thank you, sir.
Thank you. Chalo, see you tomorrow early morning. Don't be late.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Thank you.